Getting very balanced. Yes,
So, one student had couldn't find his homework 5, and went to Rosita, and she doesn't have it. So maybe someone picked it up. So if you happen to have Sue Jun's homework in your homework, or accidentally picked it up or something, if you could just give it back to me, that'd be great.
Okay. Are there any comments or questions? Yeah.
Does the labs towards the same point?
Are the labs the same point? Yeah. There's how much is the labs?
Most of the homeworks are 24 points, and the last lab was 30, so it's slightly more.
How much is this lab? Probably
this
30.
one will probably be, actually this one has fewer questions, so this will probably be 24 also.
There's 4 questions, so it'll probably be 24, right? Yeah, there was a little bit of confusion among some of the students. You're not supposed to do the lab together. In other words, you can't just start with the problems. So you do that, I do this, and then we'll hand it in the total solution. So do not do that. Okay. Okay. So the next lab is actually on, but that's due next week. It's on optimum FIR filter design, and it's also on bilinear transformation, which is a topic I'll talk about today. So where we're going with the lectures is that I'm gonna wrap up the discussion on the impulse invariance technique as a way of designing IIR filters. And after that, I talk about a different transformation, bilinear transformation. And then after bilinear transformation, as applied to low-pass filter, we talk about bilinear transformations for high-pass. And then we'll move on to talking about direct techniques for designing IIR filters. Then when we're done with IIR filters, I'm going to talk about DFTs and FFTs. And I know I've done some show of hands in class before on that, but the audience is different. Some of the students have dropped out, and so I'd like to take sort of another show of hand, either now or when we get to that part, to get a better understanding of how much you guys know about DFTs and using DFTs to do convolutions and FFTs and topics like that. So maybe it's a little bit too early. And depending upon if I feel that, in fact, one of the things I might do is just give a homework on that. Well, I don't know if that's a good idea. Just give a homework to test your abilities. That's a mean way of doing things. Let's not do that. Maybe come up with a pop quiz that doesn't count for anything, just for me to get an understanding of how much you remember about DFT, so that I can give it the appropriate coverage. I don't want to spend too much time on it. On the other hand, if you don't know it, of all the signals and systems classes you took, and of all the topics you covered in all those classes, DFT is just about the most important one. It's the one that you use in practice to do something useful with it. So if you don't understand it, or if you don't know it, then it's really a pity. So there's a balance that has to be cut there. This is what's hard about teaching this course, is that there's a lot of varied backgrounds here, and no matter how I teach it, there's somebody who says there was too much overlap or repetition compared to 120, and some people say it was too fast if I teach it the other way around. But anyway, let's talk about filter design. So what I talked about last time was we're concerned with designing IIR filters with rational transfer function, and rational transfer functions, that means you have ratio of polynomials as their h of z. So filter design essentially boils down to determining the coefficients of those polynomials, right? Then I talked about desirable properties of one of the techniques to do that is transformation technique, and within transformation technique there's the impulse invariance and bilinear. And before we even start talking about impulse invariance, I talked about desirable properties of transformations. We want causal and stable analog. Well, first of all, the transformation technique involves these 4 steps. If you can put the camera here for just a sec. This is all from last time's lecture. You're given a set of specs. You transform the specs from discrete time to continuous time, from Z to S. You design the continuous time IIR filter, H sub A of S, which is the analog filter, and then you transform it back to the discrete time to get H of Z. Then we talked about a variety of continuous time filters, Butterworth, Chebyshev, and elliptic. And then we talked about desirable properties. One of them was that you want a causal and stable analog filters to transform into causal and stable digital filters. You want the j omega axis in the S plane to get transformed into either j omega circle in the Z domain, so that you can do the mapping of the specs between the 2 domains easily. And finally, you want rational transfer functions in the analog domain to correspond to the rational transfer function in the discrete time domain, so that you can end up with implementable filters. And what we proposed was this impulse invariance transformation, which is essentially this. You start with an analog impulse response. So you sample it at every t seconds, and you get h of n. And we went over the properties of that. We found out that it does transform a causal stable analog filter into causal stable digital filter. And we also found out that it transforms a rational transfer function from analog to digital and vice versa. And in terms of j omega axis in this S-plane, to get transformed to the e to the j omega circle in the Z-plane, this is the relationship that governs between the Fourier transform of the discrete time filter and Fourier transform of the analog filter. And this comes from the beginning, and if there's no aliasing, then this thing pretty much holds true, and you can translate the specs. But if there's aliasing, the specs in the process of getting translated might get messed up, and therefore, even if you design a filter that satisfies the specs in the analog domain, it might not exactly satisfy the specs in the discrete time domain. Okay? In which case, you have to increase the order of the filter or fudge around with it a little bit more to get it to happen. Where we ran out of time was this example. Okay? We talked about design using impulse invariance. So this was the set of specs we were given, shown here. We translated this specs to continuous time. We chose arbitrarily t equals 1, and you'll see in a second that it just doesn't make any difference. As long as you choose the same t in step number 4 to undo the transformation, everything just balances out. So the filter here, actually, if you come late, hold on. If you come late and you're handing in your homework, it's very disruptive to my talking when you come in and you drop the homework right in front of my desk. So if you are late, first of all, don't be late. But if you are late, you go around, come back the other way, and go to this other table. Thank you. So we're translating the discrete time specs into the continuous time specs, and we chose t equals 1. And this becomes the specs, the same identical thing as we had here, right? If we had chosen t something else, then there would be a scaling factor between this omega and that omega, and it would have been different, but we chose t equals 1, so it's the same specs. And then we designed our Butterworth filter, and the way we designed the Butterworth filter, we said, look, because Butterworth is a monotonically decreasing type of a filter, then we're going to require it that at the passband edge, i.e. 0.2 pi, to pass through this point, and at the stopband edge, we're going to require it to go through this point. If we make it do anything else, if we make it go above this point in passband and below this point in stopband, it's going to result in unnecessarily higher order filters that's undesirable, right? So these are the two constraints that we imposed. At passband, it goes through 0.89. At stopband, it goes through that. And then I gave it a little tutorial about Butterworth filters. The magnitude square of it is of this form. And if you have a Butterworth filter of order n, let's say in this case order 6, for example, then you can put 12 poles around the unit circle, and the poles that are in the left half plane, the 6 of them that are in the left half plane, 12 equally spaced poles around the circle of radius omega c in the S plane. And of those 12 poles on that circle, the 6 to the half, or n of them, 2 to the n total, n that are in the left half plane, those are the ones that end up being part of the Butterworth filter, that causal stable Butterworth filter that we're all after, right? For the analog filter to be causal and stable, the poles have to be on the left half plane. That's why we choose these and not those, right? So there's 12 of them. If I have ordered 6, n equals 6, you've got 12 equally spaced ones, in this case 30 degrees apart, and you pick the 6 on the left, and those are the poles, and the radius of the circle is omega c. Yeah.
Do the poles can they lie on the imaginary axis?
No. They're equally spaced, but in such a way that they don't lie on the imaginary axis. You can see the way I drew it. There's many ways of putting 12 equally spaced points around this circle, and I've done it in this way, and this is the way it's done for all orders. Question?
So how did you choose 12? Was it just 2n? How did you know
Yeah,
for
this is an example for n equals 6. A 6th order Butterworth filter will have, I first put 12 equally spaced things around it, and then I pick 6 to the right. If n was 8, I have 16, and I pick 8, right? This is just an example. It could be n could be any number. So here's the thing. So I go back and I said, now that I know the shape of my butterworth filter is 1 plus omega over omega c to the power of 2n. That's magnitude squared. So let me just plug it in. I have two equations, two unknowns, and that gives me n equals 5.88, omega c equals 0.704. And I think I might have gotten some of these numbers not exactly right, but that's almost immaterial. So that results. Well, we can't have an order that's a fraction. So we need to have an integer. So we round up 5.88 to 6. And if you round that up, then there's two. Then you have to find out the new omega c, and you can either plug into this equation or plug it into this other equation. And this is really when we ran out of time, and I might have explained things in too much of a hurry last time. So, question is, which one of these two? Depending upon which one I plug in n equals 6, I get two different values of omega c. And so the real question is, which one should I pick, the equation 1 or equation 2? If I pick equation 1, essentially I'm enforcing my frequency response at 0.89, at 0.2 pi to pass through 0.89. If I pick equation 2 to find omega c, then I'm enforcing that at 0.3 pi, which is the stop band frequency, my frequency response to pass through 0.177. So pictorially, if I pick equation 1, at pass band I go through this point, but at stop band I'm going to be over satisfying the specs. Why? Because n was 5.88 and I'm jacking it up to n equals 6. That's why I over satisfy. And I did that on purpose to make sure that I don't miss my specs. So case 1, if I plug into equation 1, I get this equation. If I plug it into equation 2, I am ensured that at 0.3 pi here, which I didn't label, let's just do that. I'm ensured that at 0.3 pi, I pass through this point that I have to pass. However, at 0.2 pi, I've over-satisfied the specs. And we decided, because we were trying to minimize aliasing, for impulse invariance, there's not exactly a one-to-one mapping between the j omega axis and e to the j omega circle. To minimize aliasing, we're better off doing that, because the faster this dies down, the lower the chances that aliasing will occur. So we plug it into equation 1, and boom, we got a new value of omega c. And so just continuing in that example, now that I got a new value of omega c, now let's just go back to our filter design. So this is the end of last time's lecture, and this is going to be the beginning of today's lecture. So now that I computed this new value of omega c, I'm done. Essentially, I'm done with step 2, which is design my analog filter. So done with step 2, i.e., I've designed now my analog filter. Okay. So what is my analog filter, and what can I say about my analog filter? Well, what I know is the Butterworth filter has h sub a of omega squared is 1 over 1 plus omega over omega c to the power of 2n, which is another way of saying the same thing about Butterworth filter, is that h sub a of s times h sub a of minus s is 1 over 1 plus s over j omega c to the power of 2n. Okay, so this is the analog. This is the Butterworth filter with the poles on the left half plane. This is the Butterworth filter with the well, not a Butterworth, but this is the filter with the poles on the right half plane. And the fact that magnitude squared is like that is consistent with the fact that the h sub a of s times h sub a of minus s is this. And so if I were to plot things, now that I got new omega c and new values of everything, for n equals 6, I draw my circle again. I put my poles again. So now the radius of this thing, omega c, is 0.7302. And the poles are again the same places as they were before. Okay. And I pick these. These are the poles that I pick for my filter. And so therefore, what can I say? I can say h sub a of s, based on all of these. Can you zoom up so that this picture is shown here? Yeah, great. So based on all of this, then I can write down h sub a of s. I would then know the location of this pole, this pole, this pole, this pole, this pole, this pole, because I know the radius of this circle and I know the angle. This angle is 15 degrees, and the angle between every two of these guys is 30 degrees. So I can figure out the location for S1, S2, S3, S4, S5, S6, and that's all there is to it. This is a filter with 6 poles at these locations. So when I plug in all of that into this whole thing, and by the way, what else can I say? Well, S1 and S6 are complex conjugates, right? S2 and S5 are, and S3 and S4 are, and therefore I can combine the complex conjugate pairs and combine them together, and what I get is something of this nature. S squared plus 0.364s plus 0.494, and then S squared plus 0.954s plus 0.494 times S squared plus 1.358s plus 0.496. And I don't know if these three bracketed terms, I forgot which one corresponds to this pair, that pair, but each one of these corresponds to a pair like that. And the reason they have real coefficients is because these are complex conjugate poles, right? So now we're done with this, and now we move on to the last step, which is I'm sorry, so we're done with the design of the IIR analog filter. That was step 3. That wasn't step 2. Now we move on to the last step of transforming this back to the digital domain. So remember, t was 1 in our transformation, so we keep that same value. So now we're going to use that to transform h sub a of s to h of z. Okay, and what we get is h sub a of s. You can write it as summation over k. Remember, this is from last time's lecture. A sub k is over s minus sk's. That means h of z is just summation over k of a sub k over 1 minus e s sub k t, z inverse. And I can then just do, because I know these s sub k's are just these poles, right? 1, 2, 3, 4, 5, 6, and I can come up with h of z. And if I do that, then I get a polynomial h of z that I have to treat and look it up in the book. If that same example is still in the book, to write down the exact expression of it. Let's see what it is. I don't know if this example is even in the book. Let me quickly check. Yeah, I think it is in the book. Is it? Yeah. Yeah, it is pretty much. So I'm going to just cheat and copy the expressions, but just so that you know, let's come back to this page if you can zoom up. Yeah. Here, S1 and S6 are given by minus 0.182 plus or minus J 0.679. And then S5 and S2 are given by minus 0.497 plus or minus j 0.497. And does that make sense? Yeah, because they're smack at 45-degree angle, right? This angle is pi. No, this is 90 degrees. That's another 15 degrees. That's 105, and that's another 30 degrees. That's 145. So for these guys, this ends up being at a 45-degree angle here. So their x and y values are the same. That's why you have 0.497. And then finally, S3 and S4 are given by minus 6.79 plus or minus j 0.182. Okay? And the angle, the omega c is 7032, not 7302. Okay? And so that gives you the so plugging into this, at the end of the day, h of z is just incredibly complicated expression, 0.2871 minus 0.4466 z to the inverse over 1 minus 1.2971 z inverse plus 0.6949 z to the minus 2 plus minus 2.1428 plus 1.1455 z inverse over 1 minus 1.0691 z inverse plus 0.3699 z to the minus 2 plus 1.8557. I think that's why I didn't want to write it down in my notes because it's so cumbersome. Minus 0.6303 z inverse 1 minus 0.9972 z inverse plus 0.257 z to the minus 2. So this is the final filter. So this corresponds to one pole pair, another pole pair, and another pole pair. Okay? And if you now look at the frequency response of this guy, now you can show figure 7.5 in Oppenheimer and Schaefer. If you look at it, this is the filter we end up getting. Zoom in, please. Yeah, this is the magnitude response. This is a sixth-order Butterworth filter transform impulse invariance type thing. This is the can you focus, please? Thank you. Can't get it focused. That's the amplitude, and that's the group delay as a function of radiant frequency. Okay? So the reason I'm showing group delay is because what? Is this a constant group delay? No. Did we design it to be constant group delay, or did we know it's going to be? No. If you don't design something for any specifics, it's not going to do it. Okay. So does it satisfy the specs? You'd have to actually test it, and there's no figures I can show you to convince you that it satisfies, but it does satisfy the specs. Would it have satisfied the spec if I had picked the other equation so there would be a little bit more aliasing? Maybe yes, maybe not. What if it hadn't satisfied the spec? Even in either case, there's a little bit of residual aliasing going on, right? What if it hadn't satisfied the specs? What would you do? You can certainly use bilinear transformation, which is a bit of a more surefire thing. But how could you fix this thing if it didn't satisfy the specs? You do the transformation back, you get your h of z, you plot it, and it doesn't do what you wanted it to do because, and if it doesn't, what would be the reason? Because of that aliasing thing, right? The transformation of the specs. What would you do? No. It turns out if you make t equals 2 and go through the exact same thing, you get the exact same answer. And I'm going to have you do it actually as a homework assignment. Dan, is it in this lab? No, it's not. Well, actually, I think it is. Is it in this lab? No, we just give him another homework assignment the following week. It just doesn't make any difference. It cancels itself out. Believe me. I know it's counterintuitive, but it really does. No, jacking up t equals 2 will not do the job. It gives you this exact same answer. What would you do? Yeah. Well, in the analog filter thing, what can you do here? Tighter what? Yeah. For example, instead of 0.177, make it tighter, or jack up the order. Yeah. That's really what it boils down to. Is that from an approximation theoretic point of view, fundamentally, you can't ask a polynomial of order 6 to have infinitely sharp transition and brick-like behavior. That's what's so fundamental. If you're given a function to approximate, and that function is brick-like, we can never approximate a brick. The only way to do a real brick is to have a sinc function, and that sinc function doesn't have a rational transfer function, and it's IIR to death. So forget that. If you want to come up with something that has the sharper the specs are, the more stringent your specs are, the more you demand of your filter, the price you pay for it is more coefficients. The order of the filter has to go up. When n goes up, there's more coefficients. When we had n equals 6, then you have 3 of these guys, and you have 3 of these guys. And these, you can think of these coefficients as sculpting or shaping the frequency response. If I jack up, make n equals 8, I got 4 of these, and I have more knobs, and I can shape it better. It's like this. When you were kids and you had like clays to play with, if you got clays of 4 clays, you can build so many things. If you got 8 pieces of spherical clays, you can build more things. You got 16 of them. Or Legos. The more you have, the more complicated things you can shape. The more coefficients you have here, the more degrees of freedom you have, the more chance you have to shape your brick-like filter and to make your transitions really narrow. So at the end of the day, approximately, if you really wanted to have a very tight transition with, like, from 0.2 pi to 0.21 pi, for example, which is really a hard filter design, the price is you have a lot of these S terms, you have a lot of poles, you have a high order, and you have a lot of these terms here. No, there's no magic. Yeah.
So just kind of from a practical aspect,
Mm-hmm.
How many taps do you normally see in digital filters? Is there a range
It's
like this? Is
highly
10,000?
It highly depends on what application you're doing. Highly, highly, highly. Like, for example, I tell you in video, which is an area I know, you can do half a pixel interpolation, you can do a quarter pixel interpolation, you can do an eighth of a pixel interpolation, but people normally don't use more than 6 or 7 taps. Most of the time, they do use FIR. For video and images, IIR is dead anyway. It's mostly FIR. For control applications, I don't know. It depends what kind of a frequency response you want to ship, and depends what kind of a DSP chip you have to crunch all these numbers. At the end of the day, if you only have a 20 megahertz DSP chip that can't, and it has to be 20 megahertz because otherwise, I don't know, it'll be too big or too hot or too much current or too much power. Or there's so many external requirements that dictate what you design that you end up not having too many choices. You just say, okay, with that amount, that's how many coefficients I can have, and this is the best response I can give you. Right? You also have to worry about, that's one topic we didn't really talk about in detail. These numbers that I wrote down to many, many digits of precision, in real life, you're going to have to quantize them. You not only quantize these, but you also have to figure out, I think we've talked about this before, about the register length for your arithmetic units. Is it going to be 8 bits, 16 bits, 32 bits? If you're not careful, if the precision is too coarse, and I think you've done a lab on this, correct? Did you? I can't remember now. If the precision is not good, these poles, because of quantization effects, not only because the coefficients are quantized, because the arithmetic is quantized and finite precision and fixed precision, they could gravitate towards the j omega axis and cause all kinds of stabilities. So in the z domain, they could go outside the unit circle and cause all kinds of stabilities. And you could, if you're in the analog domain, that's one of the reasons people walked away from analog. when your circuit heated up, the effective poles would have moved, and then without you knowing it, the thing could become unstable. And that's very important in, you see, in electrical, you could argue in electrical engineering when the thing becomes unstable, what really happens? If you had an op-amp, it'll hit the rail voltages, right? Plus or minus 5, plus or minus 12, and boom, you walked away from the linear mode, and now we're in the unlinear mode. The transistor got to be unstable or something. The circuit got to be unstable. Mechanical engineering systems, and that's to your credit, the mechanical engineers, the helicopter becomes unstable, you crash and die. That's the end of it. Yeah, I mean, it's very serious. And think of instability in in mechanical engineering. A typical example is helicopters. They're marginally stable system. Their poles are on this J omega axis by design, not because we did something wrong. And so think twice before you ever get on a helicopter. I think the first time I got in it, for the first 30 minutes, I kept thinking, what kind of life insurance did I choose when I joined UC Berkeley? And then to make matters worse, the pilot said, oh yeah, the guy who used to do this before me, he had a heart attack last week in the middle of the air. It's like, oh my God. Anyway, and high performance systems like the ones the military builds, high performance, they're really designed to be on the borderline between stability and instability, and that's how you get a lot of performances. You can have you can optimize performance by pushing things to the limit, but the consequences could be disastrous if things get unstable in mechanical systems. Okay? And you all know what marginal stability is, right? When the poles are sometimes in mechanical engineering they refer to it when the poles are on the J omega axis. Okay? Yeah.
Why does picking the 6 poles on the left not change the actual filter? So we don't care about the poles on the right, or?
The Butterworth filter is this, by definition. And the reason I put all the poles on the circle so that I tell you how I came up with them. You know what I mean? So n equals, whatever n is, I multiply it by 2, 2n, and I divide, the spacing between the poles is 360 degrees over 2n, always. Now, with those poles, you can put them anywhere like that. I'm not telling you how to put it, but now that I've drawn it, I'm telling you is that if I call this angle alpha, that not only the angle between any two poles, any of two of these dots is alpha, but the angle between this and this is always alpha over 2. So I'm now uniquely specifying how you put your 2n poles around it. And then I'm telling you, once you put all the dots around the circle, the actual Butterworth filter, the causal stable one, only has these as the poles and not these guys. So I'm trying to uniquely, in a geometric way, specify to you where the poles are, right? So this is alpha over 2, and this is alpha over 2, so the whole angle is alpha. And this angle is alpha. And this angle is alpha. And this angle is alpha, etc., right? So you start with whatever the order is, n, multiplied by 2, divide 360 by that, and that's the degrees. So that sort of uniquely specifies the location of the poles of a Butterworth filter.
So if we do increase the order, the angle is smaller, potentially come closer to
That's force for stability, but if that's what you want, a really sharp thing, yeah. You have to do it. And if you don't, and the coarser your quantization is, the more perturbation they get when you quantize from the real place when you quantize them, and the shorter your word length is in your implementation, the worse it becomes.
So do we start to see peaking in the filter response as the poles approach the J omega axis
A little
as
bit.
you increase the Butterworth order?
Yeah, you do. Yeah. Maybe at what exact value will it be noticeable? That's, you have to experiment and play with it. Okay. Any other questions? Yeah.
Why do you need your poles to be equally spaced? Because you really want to approximate where this in the transition band.
I didn't require it to be equally spaced. That I used Butterworth. I could have used elliptic or I could have used Chebyshev. But because I used Butterworth, this is a characteristic of a Butterworth filter. I didn't need it to be like this. But here's an easy example of analog filter design. I could. The good thing about Butterworth, because it's monotonically decreasing the passband stop and it's easy to understand, so that's sort of what I use as an example. You could have used anything else. Okay, yeah, one more.
It seems like you need a D to C and C to D converter to implement this whole thing. So isn't this kind of wasting?
No, it's not. You don't really need a D to C or C to D. It's only a design conceptual steps that we went through. Real life, you want to. It's a paper and pencil design. The end goal is to come up with this H of Z, to come up with these coefficients. And so in paper and in concept, in your head, you went through all of this, but at the end, you came up with this. Now you go ahead and build your, summers and delay elements, and you translate that into a difference equation, and you just build it, right? You can build it either with discrete components or with FPGAs or with, DSPs or something like that. In a sense, you're right in that we translated a problem that we didn't know how to solve into something that we did know how to solve. So you can say we chickened out, which we did. But that's how a lot of work in science and engineering gets done, right? Transform your problem into something you do know how to do. Okay, so let me move on to bilinear transformation. Okay, great. Bilinear transformation. So that's still part of this whole paradigm of transformation design, which we talked about last time, which is summarized in this page, right? It's nothing terribly different. You're given a set of specs. Now I'm talking about another way of doing this transformation in step 2 and step 4, right? All the other steps, 1 and 3, are the same. Before I used impulse invariance transformation, now I'm going to talk about bilinear. And sort of the motivation for bilinear is that it's a bit more of a sure shot because it doesn't have that aliasing thing we talked about, because it really does map the j omega axis in the S plane to the e to the j omega circle in the Z plane. And so how it works is this. I'm just going to tell you how I transform an analog filter H sub A of S to this digital filter. So I'm just going to replace S with 2 over T, 1 minus Z inverse, 1 plus Z inverse, and that's how I get my H of Z. And I put a little D because D is for discrete time. So here's the proposal. This is what bilinear transformation is. And I'm going to spend the next maybe 20 minutes or so convincing you that it's a good transformation. It has all the desirable properties that we're after. Well, first of all, this is already rational, right? S and Z are already related to each other in a rational way, a ratio polynomial to another ratio polynomial. So clearly, if I start with the rational transfer function and I replace it in S and I replace all the S's with this rational transfer function, I'm still going to get a rational transfer function for H sub D of Z. So the first observation is that because it is rational, in other words, S equals 2T over 1 minus Z inverse over 1 plus Z inverse, a rational transfer function gets transformed into a rational rational transfer function in continuous domain, in continuous time, gets transformed into a rational discrete time transfer function. Okay, so that's good. The second question is, does the j omega axis get mapped into the circle? In this e to the j omega in the z domain? Well, we can just try and see what happens if we let z equals e to the j omega. So let z equals e to the j omega and plug that into this relationship. So you get s equals 2 over t. And by the way, t is some arbitrary parameter, or that you'll see the effect of it in just a minute. So it's 2 over t, 1 minus e to the minus j omega, 1 plus e to the minus j omega. Okay. So what can we say about these things? Well, why don't we factor out e to the minus j omega 2 in the numerator and denominator, and what we get is the following. We get s is equal to 2 over t, e to the minus j omega over 2, e to the minus j omega over 2, and then e to the j omega over 2 minus e to the minus j omega over 2 in the numerator, and e to the j omega over 2 plus e to the minus j omega over 2 in the denominator. So I'm just factoring out this. And why did I do that? Well, because now I got complex conjugates inside here, and I got complex conjugates inside here. So what I get is 2 over t. These two guys cancel out each other. This one ends up being sine omega over 2. This one cosine omega over 2. So I get, and then there's a j factor, 2 over t j tangent omega over 2. So what can I say about that? Well, s is equal to sigma plus j omega. This is our s-plane, right? That you're used to in Laplace transforms and other things. So putting all these things together, what can I say? What does sigma get mapped to? So in general, if I started off with letting z equals e to the j omega, and I plugged it into this, and this is the mapping. These are the s-planes that get affected essentially what this is happening is this. The interpretation of this is this. This is e to the j omega circle. So when I'm at omega equals 0, I plug into this, and that tells me what s I get. And as I change omega and traverse along this circle, plug into this, and I keep getting different values of s. Right? That's what this is telling me. This is what the meaning of this is, right? So what can you say? What trajectory do I traverse in this s-plane as I change the value of omega and walk around the e to the j omega circle? Am I going to be all over this plane?
No, this is imaginary one.
I'm only going to be, because this thing is purely imaginary, no matter what I do to omega, if it is 0, pi, pi over 2, pi over 6, pi over 8, no matter what omega is, tan omega over 2 is a real number, times j, that's an imaginary number, s is, no matter what the value of omega is, s is a purely imaginary value. So based on this, as omega goes from 0 to 2 pi, s, in the s-plane, we only traverse the j omega axis. In other words, what I'm trying to say is sigma equals 0. And omega is equal to 2 over t tan omega over 2. So as I traverse here, it gets mapped into here. So this thing, in some sense, gets mapped into that thing. Okay? And so that's perfect. That just satisfies the thing we wanted to do. We wanted J omega axis to have a mapping inside this. So it just does it. And what can we say about what can we then say about causality and stability? Can we be sure that a causal and stable a filter gets transformed into a causal and stable filter? Well, we need to show not that this circle gets mapped into this axis. In order to show that a causal stable filter in analog gets mapped into causal stable into digital, all we have to show is that the left-hand side gets mapped inside of this circle and the right-hand side gets mapped outside. Why? Because all these transformations are smooth and continuous and differentiable and all these other nice properties. If this gets mapped to this, then the left-hand side either gets mapped inside or outside, right? Because of smoothness properties. The only question is which way is it? If the left-hand side got mapped to the outside, we're in trouble. If the left-hand side got mapped to the inside, we're okay, right? And again, because of smoothness and continuousness and all these other things, it's sufficient to just test it for one point. If one point here gets mapped into one point inside, we're done, right? So it's very easy. Just pick your favorite. Pick S equals, I don't know, minus some number here in this region and show that it maps inside, and you're all done. So let's write all of that thing down. So question is, does causal stable H sub A of S gets transformed into causal stable H of Z? That's the question. We need to show that the left half plane in the S domain is mapped onto inside of the unit circle in the Z domain and not outside of it. If it's outside, we're in trouble. And to do that, we only need to show it for one point. Why? Because of smoothness and continuity of it. So pick a point in the left half plane in the S domain in left half plane. Let's say S equals minus 2 over 3 over t. Just any point. This is the S plane again. Let's say here. Right? Then plug it into our transformation. S is equal to 2 over t, 1 minus z inverse, 1 plus z inverse. Then it's equal to minus 2 over 3t. So S is equal to that. What value of z does it correspond to? Well, I deliberately picked this to be t, so these t's cancel out. And what I get is z equals 1/2, which is exactly inside the unit circle. This is the z plane. Which means that magnitude of z is indeed is smaller than 1, And you got it inside the... So essentially we've shown that causal stable H sub A of S, so this is causal stable H sub A of S results in causal stable H of Z, H sub D of Z. D stands for discrete, not desired. And furthermore, if I were to plot this relationship here, which is omega equals 2 over T tan little omega over 2, what I get is something like this. This is 0. This is pi. It's just a tan relationship, right? At omega, little omega equals 0, I get 0. At omega equals pi, it just blows up to infinity. And does that intuitively make sense? Absolutely. Why? Because in discrete time domain, omega equals pi is your high frequency, and there's no higher frequency than omega equals pi, right? And then in continuous time domain, what's high frequency? Capital omega what? Infinity. So this thing is dead on. It's exactly what we wanted to happen. It makes perfect sense. So now that we have this transformation, let's just, how does this thing help us in step 2 and in step 4? In particular, in step 2, when I want to transform my specs from discrete time domain to continuous time domain, that's the transformation I'm going to use. Here's how. So here I am. Somebody has given me this set of specs in discrete time domain. It says, look, I want you to design an H of omega that has ripple is between 1 and 1 minus delta p in the pass band, and it has ripple of delta s in the stop band, and this is pi, and that's it. That's my specs in the discrete time domain. And how do I, using this transformation, bilinear transformation, how do I design my filter? Well, let's plot that. This is omega, this is capital omega, that's the thing we just had. This is pi, 0. I'm just copying over this thing that I had a second ago. This is our transformation, which is 2 over T tan omega over 2. And now I can easily use these two plots to come up with my specs in the continuous time domain. It's a function of omega, H sub A of omega, magnitude. So how do I do that? Well, let's first transform these two, omega p and omega s, the pass band frequency and the stop band frequency. So how do I do that? Start with omega p, go all the way up here. This is the omega axis. This is omega p. And go all the way up and see where it hits the curve. And if it hits the curve, we call the place it hits the curve, we call it capital omega sub p. Okay? I drew this wrong. I'm going to recopy everything. Recopy everything except just erase this. Sorry about that. Okay, what I meant to do is draw it like this. And okay? Okay, so that's H sub A of omega. And so let's just transform the frequencies. This is omega p. It hits this axis is also little omega. This is also little omega. And I go all the way up. And I now transform my little omega p into big omega p. I call that and I go all the way up, and that's big omega axis, so that's big omega p. So that's it. Using this curve, I figured out how to transform this to that. And then omega s, the same thing. So that's my new omega s. Given a value for this thing, that's 2 over t tan omega over 2. Okay? And what this is saying is between, what this spec is saying is between, for omega values, between 0 and omega p, I want the ripple to be between 1 and 1 minus delta p. So this is 0, this is omega p. I want the ripple for this range of frequencies to be between 1 and 1 minus delta p. And for this ripple values, for omega s onwards, where is pi? Pi is like, all the way, omega equals infinity. So from omega s and onwards, it goes all the way to plus infinity. I want my ripple to be omega s. So that's the specs for my new analog filter. Okay? And I can yeah. So how does this then work in terms of, so this is how translating the specs from analog, from discrete time to continuous time works, right? So now let's actually go over an actual example and show this thing in action. It's not all that different from the impulse invariance technique that we just talked about earlier in this class. So as an example, we're given some sort of a spec, which is of this form, magnitude of h of omega. That's supposed to be between 1 and 0.7. And it's supposed to have ripple of 0.2 from 0.5 pi onwards. This is a discrete time specs. And just roughly, do you think this filter is going to need a higher order or lower? Or if we were going to stick to Butterworth like we did for the example we had for impulse invariance technique, do you think this is going to be requiring a higher order or lower order than n equals 6? Yeah, lower order. And why? The specs are a lot looser. Before, we were going to have to transition from 0.2 pi to 0.3 pi. Now we have 0.2 pi to 0.5 pi. So transition width is literally 3 times as big. Before, we had a tighter spec here. The ripple had to be smaller. Now the ripple is bigger. And this ripple is bigger than it was to be. So and all, across all dimensions, no matter which way you look at it, the thing is just, it's a looser set of specs. So you sort of expect to get a lower degree thing. So I want to convert these specs to discrete time, from discrete time to continuous time. So again, for convenience, I pick t equals 1. So then what happens is that omega is equal to 2 over t tan omega over 2. If I let t equals 1, then I get omega equals 2 tan omega over 2. And what happens is that if I let omega p equals 0.2 pi, that means omega p is 2 tan 0.2 pi over 2, which is 0.6498. And if I let omega s be equal 0.5 pi, that means capital omega s is 2 tan 0.5 pi over 2, which is equal to 2 tangent of 0.25 pi, which is a quarter of a pi. And what's tangent of quarter of a pi? 1. So 2 times 1, you get 2. So we've just plugged in these little omega p's, and based on this transformation, we get these capital omega p's. And how do you do it then? So what does the specs look like? Well, as a function of omega, h sub L of omega, here's omega p, here's omega s. Omega p is 0.6498, and omega s is 2. And in what units are these? Radians. So coming back here, these are the only 2 points that changed. So between 0 and 0.2 pi, I want it to be in between 1 and 0.7. So between 0 and this, I want it to be 1 and 0.7. And between here and here, I want it to be the same thing as it was before, which was 0.2. So this is 0.2. Okay. And so that's my specs. That's the pictorial depiction of my specs. Now I have to move to step 3 and actually design my IIR analog filter. Yeah, in all of these things. There's no reason to change it, right? So how do I then design my analog filter? Well, go back to the same set of arguments as we had before, right? Use Butterworth, so h sub A of omega squared is equal to 1 over 1 plus omega over omega c to the power of 2n. And I'm going to force my Butterworth filter to go through this point and to go through that point. And if I do that, what do I get? Well, so to pass through omega p, I get 0.7 squared is equal to 1 over 1 plus, and what's on my omega p? 0.6498 over omega c to the power of 2n. And then to pass through the omega sub s point, I get 0.2, because that's the thing here, squared is equal to 1 plus 1 over 1 plus, and now omega s is 2 over omega c to the power of 2n. So I combine these two things, and I get n equals 1.3957, and omega c equals 0.6405. And in this bilinear transformation, because there's no aliasing, there's no buts and ifs or anything like that. So if you do everything right, everything will work out. Now, n equals 1.39. Shall I reduce it to 1 or shall I reduce it to 2? To 2, because if I reduce it to 1, there's no chance in hell it'll satisfy the specs. Nobody, there's no leeway, there's no margin here for the specs to be satisfied if I move down to 1. All right? Everything is very precise. You know, everything is, we're sort of, given that we're stuck to Butterworth, I'm not saying Butterworth is the best way of designing analog IR filters, but given that we're sticking to that, no other miracle will come to, if I reduce this to 1, to make the specs be satisfied in the discrete time domain. Yeah.
From the small omega to the big omega equation, it seems to me when small omega is small, the delta W will be smaller.
Which will be smaller?
The transition width for the big omega will be smaller than the original one. The original in the discrete.
Well, those are two different things. One is discrete, one is analog.
Yes, so if you compare that to the original, the one we just used, the
oh, I see. You're saying the specs is tougher.
Yeah. Will that add difficulties to our
possibly? But remember, you can also play with T to make these things be smaller. I guess what he's saying is that if in this filter we're going from 0.6498 to 2, And in the filter from, in the analog domain, what we're going is from 0.2 pi to 0.3 pi. So the transition width here is 0.1 pi, which is 0.3 in radians. Here is actually quite a bit larger.
Because the spec is different.
Yeah, yeah. Anyway, let's wrap up this. So here I can't really make n equals 1. If I do, it won't satisfy the spec. So I pick n equals 2. The question is which equation to use for omega c, equation 1 or equation 2. And the answer is it doesn't make any difference. There's no aliasing to worry about. You just pick either one you like. Okay? So it makes no difference. And if I just use equation 2, which is this guy, then I get omega c is equal to 0.6437. Okay? And so n is equal to 2, and so I have a second order Butterworth filter, right? And how do the poles for a second order Butterworth filter look like? N equals 2, 2n is equal to 4. I pick 4 points equally spaced around the circle. What is the angle between them? 360 divided by 4 is 90. And how do I pick them? Well, we just went over that a second ago. The distance between the poles is 90, but I pick them such that this is 45 and this is 45. So where they are is here, and here, and here, and here. Okay, there's 90, 90, 90, and 90. And these are the poles for my Butterworth. So this is, if I call this S1 and I call this S2, S1 is equal to minus 0.4549 plus 0.4549J, and S2 is minus 0.4549 minus 0.4549J. They're complex conjugates. So n is equal to 2, 2n is equal to 4. The angle between these things is 360 divided by 4, which is 90 degrees. And the 90 degrees, again, the way I put them is 45 up here, 45 down there. So hold on a second. Let me wrap this up and ask the question at the end. So what that then means is H sub A of S is just has one second order term. It's 0.6437 squared over S minus S1, S minus S2. And because S1 and S2 are complex conjugate, like we've shown here, this is going to be a polynomial of second order with real coefficients. And finally, step 4, converting it back. Now I use the very transformation that I came up with. S equals 2 over T, 1 minus Z inverse, 1 plus Z inverse, because I use T equals 1. I continue to use T equals 1, and I get from this H sub A of S, I get my H of Z, which ends up being something like this. This is all, I think this example is in the book. So that's my final filter. Question? Yeah.
You were saying something like there's no aliasing, so I'm wondering what the difference is between, because in the previous case there was aliasing, right?
Because the J omega axis in the previous case, in the S domain, didn't get mapped to the unit circle. In this case, it did. Right? When you start with a continuous time impulse response and sample it, and that's how you get your discrete time filter, the relationship between those two frequency responses is that summation that I wrote, and therefore there's aliasing. Here, the first thing I showed was the J omega axis gets mapped to the either J omega circle. And so there's absolutely no aliasing. That means there's a one-to-one correspondence. Let me just go back, having said that. What that means is that in that filter, right here, whatever my analog filter at this omega naught, let's just do a hypothetical experiment, mind experiment. Whatever omega, there's a one-to-one mapping between each value of omega naught and omega I and capital omega I, right? What that means is if I pick an omega naught and my analog filter at omega naught takes the value, I don't know, 5, whatever the map of this guy is, let's say, I don't know where it is, but let's say it maps here, this, my discrete time filter exactly takes the value 5. Think of this as a cake, as a mountain sticking out of this, right? And the best example is like a birthday cake, where you take a knife and you cut it. Right? I cut it like that. That cut that I get repeats warp it in some way, and it repeats itself around another cake, which I cut like with a knife around this way. That function here is getting mapped into another function as a function of this omega here. Precisely. One-to-one mapping. No buts, no ifs, no aliasing, nothing. And that's the beauty of the bilinear transformation that we didn't have with impulse invariance. Here we showed that S is equal to 2 over T J tan omega over 2. As I traverse my, let's just pick values. Omega equals 0, little omega equals 0. What's tangent of 0? 0. That results in S equals 0. So this point in particular got mapped into this point. Now omega equals, I don't know, pi over 2. By the time I get to this point, what's this? Tangent of pi over 4 is 1. So I'm 2 over Tj. That's J. That's 2 over T. That corresponds to little omega being pi over 2. And then as I traverse, so if T was equal to 1, for example, that would be 2. So as I traverse here, I traverse this axis. Yeah.
So I can understand how if you have like a brick-like amplitude response, how there would be no aliasing, but how come like you can have a function that has infinite support that just goes on forever off to infinity? Like how does that get mapped onto the periodic domain?
As omega, okay, let's continue with this. When omega approaches pi, when omega approaches, so this was omega equals 0, right? It got mapped to this point. You bought that. This point got mapped into 2. As I get closer and closer to pi, what's tangent of pi over 2? Infinity. So as I get closer and closer to this, I go higher and higher up here, higher and higher and higher. This is it. That's why that's happening. This is the mapping. It gets stretched, if you will. And when I go this way, it gets stretched that way. By the way, this is called the conformal mapping. For those of you who are taking applied math courses, there's also a name for it. But anyway, yeah. I start from here. Omega equals 0 is right smack in the middle, right? As I move up here, I go ooh all the way that way. My hands was covering. As I go this way, this goes ooh all the way that way. As I go this way, I go ooh that way. Did you get it? Okay. So yeah, but it's the same function. It's the same thing, right? It's a one-to-one mapping. Don't forget to pick up the lab for next week and also solutions for this week. Yeah.